Okay, hey everybody. We're going to do another example of turning a transfer function into a state space and phase variable representation. So, if you've got a transfer function like this, powers in the top, powers in the bottom, or a large numerator with a lot of s's in it, what's usually good to do is draw a block diagram of first the numerator, plus 6s squared plus 10s plus 5, with an input of u. If you do this, then you get an output of x of some type, and then you multiply that by s squared plus 3s plus 8. So you just separate the numerator here real quick and easy. You get an output of y. And these outputs from each one of these blocks is going to make more sense here in a minute. But so if you want to do the state space representation of this, you've got the highest power is s cubed, so you're going to have a 3 by 3 matrix, a matrix, and vectors 3 long. So x1 dot, x2 dot, x3 dot. Again, I'm not going to explain where these come from. It's part of the derivation of this shortcut system, and we are going to use the shortcut. So with the shortcut, you've got a 3 by 3 matrix here of some kind, and you know, since this is in proper form, you can just take the opposite negative order of these values underneath it. So it goes -5, -10, -6, and then 0, 0, 0, 0, 0. Then you know that this is going to be 1, and that's going to be 1. Then you've got 0, 0, just like that. Did I get that laid out right? Sorry, I put another layer in there that wasn't supposed to be there. It's supposed to be a 3 by 3 matrix. So 0, 0, 1. There we go. I'm sorry, I just confused you guys. But it's 3 by 3 matrix because of the power of s. Once you do the shortcut of the reverse negative order, the off diagonal on the upper part is always 1s, and the rest of it is 0s. So you take this diagonal right above it, 1, 1, 1, so on and so forth, and the rest is 0s. And you multiply that by x bar, or x1, x2, plus the output here, which is 0, 0, 1 times u, which is, this is found by the numerator of this box, which is 1, and it's in the last last column there because that's just the way it goes. If there was something else up here or anything like that, well, no. This value right here will always be the upper value of this fraction. If this was like 30 or something, then this would be 30. And these two are always left at 0. Basically, that's pretty much the rule. Let me see if there's any exception I can possibly find. No. When you're using the shortcut method, this is the last value in this matrix will always be the numerator of this equation, which is why we had to separate these, because if this stuff was still up here, then you get all confused by what this value would actually be. But now we have to do the last part of our equation, which is y is equal to a matrix. This is basically x1, x2, x3 values. That was a horrible 3, sorry. And what you do for this is the reverse order of this, all the way up to s squared. Oh, something to mention here. You might notice that I only went up to 6 on this. So this has to be in proper form, and you don't include this in your matrix. It creates the size of your matrix, but then you ignore it as far as values. So the highest power of s is something you ignore in this matrix. So then, moving on with this, using these values up here, you have 8, 3, and 1. And you don't make these negative, it's just the reverse order. Times x bar is equal to 0 times u. And this is almost always 0. There's not really much of an exception. If you're using the shortcut, this is pretty much always going to be 0. And that's how you do it. That's how you set up a state space representation of a transfer function with s's in the top and s's in the bottom. And if you want to look it up in your nice book, it is 3.13 in the nice textbook for controls engineering.